Imagine you're standing right in front of a massive, multi-ton transformer that's meant to power an entire city block. As an engineer, your main problem is that you absolutely have to know exactly how this beast is going to behave under a full load. You need its voltage drop, its efficiency, its thermal limits, all of it. But here's the catch. You can't just hook it up to a live city grid to see what happens. That would be a highly dangerous, immensely expensive, and honestly, a pretty terrifying way to test a connection. So in this explainer, we're going to dive into exactly how we get around that.
So how do we actually solve this? Well, we use what is essentially an elegant engineering cheat code. You don't actually need to load a transformer to its full rated power to know how it'll behave under load. Instead, we're going to look at two highly specific, super cheap, and completely safe bench tests that give you every single number you need to calculate a transformer's full equivalent circuit. No massive power grids required. Just two tests, zero risk, and all the numbers.
Section 1. Open circuit, the core. Let's start our virtual lab walkthrough with the first of these two tests, which is brilliantly designed to completely isolate the imperfections of the transformer's magnetic core. Looking at the setup here, we've got an AC voltage source connected to the primary winding. We have 3 meters hooked up, a voltmeter, an ammeter, and a wattmeter, to measure the real power being consumed. But pay attention to the secondary winding. It is left completely open-circuited. There's literally no load connected to it whatsoever. Here's how it works. We apply the full rated voltage to the primary, but since that secondary is wide open, zero load current is flowing through to the other side. Because of that, the tiny bit of current the ammeter picks up and the power the wattmeter registers are entirely due to the core losses in the magnetizing current. This gives us exactly what we need for our equivalent circuit. RC is just the applied voltage squared divided by our wattmeter reading, and XM comes directly from the reactive component of that no-load current.
The big takeaway for this first test? The open circuit test gives you RC and XM, and it is always done at rated voltage. Why? Because core loss depends heavily on the magnetic flux in the core, and that flux depends directly on the applied voltage, not the load. By running this at rated voltage, we're perfectly simulating the exact core conditions that the transformer will see out in the real world.
Section 2. Short circuit, the copper.
Okay, so we've got the core figured out. Now we completely flip the script to measure the copper imperfections, meaning the resistance and leakage in the actual windings themselves. Notice the massive change to the setup. The secondary terminals aren't open anymore. We've short-circuited them together with a thick, heavy jumper wire. On the primary side, we still have our 3 meters, but this time they're connected to a fairly low voltage source, not the full rated voltage. For this test, we actually start with the input voltage at 0 and carefully, slowly crank it up. We stop the exact second the ammeter tells us that the current in those short-circuited windings has hit its full rated value. Since we are driving a dead short, it takes almost no voltage at all to push this massive rated current. And because that input voltage is so incredibly low, the magnetic core barely even magnetizes. The core losses practically drop to 0. So if we ignore the tiny excitation current, essentially all the power being read by the wattmeter is pure copper loss from the series elements. That gives you REQ directly from the power divided by the current squared, and XEQ from the reactive part of that small applied voltage. To sum up this second half of the cheat code, the short circuit test directly yields the equivalent resistance and reactance of those copper windings. And just like our first test had to be at rated voltage, this one must be done at full rated current. Copper loss, which is basically just the heat generated in the wires, depends entirely on the current flowing through them, not the voltage pushing it. Now, I want you to pause for a second and just think about the physical realities of what we just did in the lab. We went way out of our way to emphasize that this short circuit test starts at near zero voltage and is carefully raised. Why do you think that is? Why not just hit it with the full rated voltage during a short circuit test and see what happens? The answer comes down to pure physics and safety. A dead short at full rated voltage would be an absolute disaster. It would pull current many times the rated value almost instantaneously. The extreme heat generated would completely melt and destroy the transformer's windings before you could even blink, let alone write down a meter reading. Ramping the voltage up slowly from 0 lets you safely lock in the rated current at a fraction of the normal voltage. It keeps the lab safe, and it keeps your very expensive transformer from turning into a smoking paperweight.
Section 3. Building the complete circuit.
So, we've successfully run both tests. Now, we get to synthesize all this data into one unified mathematical model that we can actually use. When you look at these two tests side by side, it's pretty brilliant how perfectly they complement each other. The open circuit test gives us the core characteristics by maximizing voltage and minimizing current.
Meanwhile, the short circuit test gives us the copper characteristics by maximizing current and minimizing voltage. They perfectly isolate the exact variables we need.
And here is the grand prize. This is our resulting simplified equivalent circuit. You can clearly see the core loss branch with RC and XM sitting in parallel across the primary, drawing that tiny no-load current. And right next to it, the series impedance branch with REQ and XEQ in series, ready to model the voltage drop when a real load is applied. Just by plugging in the math from those two safe bench tests, engineers get a completely characterized model ready for rigorous operational studies, without ever needing to hook anything up to a real city grid.
Now, up to this point, we've spent all our time looking at standard, perfectly isolated two-winding transformers. But what happens if we take that fundamental rule of transformers, the idea that primary and secondary circuits absolutely must stay electrically isolated, and just throw it right out the window? Next up, Part 2, Autotransformers.
Section 4. Autotransformers breaking the rules.
We're shifting gears here to look at a device that boldly breaks the rules to unlock some incredible efficiencies. Looking at the schematic differences, a conventional transformer uses two totally separate coils. An autotransformer, though, uses a single tapped winding. The secondary literally merges partway into the primary. They physically share a section of the coil, which we call the common winding, while the unshared part is the series winding. You can see a physical cutaway of one here, often used in labs. Because the power transfers partly by direct electrical connection through that shared section and only partly through magnetic induction, an autotransformer needs drastically less copper and steel than a conventional unit doing the exact same job. It's a remarkably cheap and efficient way to tie nearly equal voltages together.
But of course, this incredible efficiency comes at a cost. That direct physical connection completely destroys the electrical isolation between the primary and secondary sides. So the big question we're left with is this. If a power surge hits one side, what exactly is protecting the other? And how does sharing this winding completely alter those internal impedance calculations we just spent so much time perfecting? We're going to uncover exactly how this direct connection changes the math and the risks in Part 2. Until then, keep questioning how things work.